I want to discuss now a second example of an MCMC algorithm for mixtures. In this case, we're going to work with mixtures of three normals, but bivariate normals. And this is going to mimic our second example for the EM algorithm. So we're going to use exactly the same data set and the same data generation mechanism, again, as a way to illustrate how our algorithm works. The true data is going to be generated from a mixture, as I said, with three components. The weights are 0.5, 0.3, and 0.2. The true means for the components are 0, 0 for the first component, 5, 5 for the second component, and minus 3, 7 for the third one. And in this case, we're going to allow the variance-covariance matrices of the different components to be different. The first one is just the identity matrix. But for the other two components, we have both positive and negative correlation. So you have seen these graphs before. We have three components that are reasonably well separated, although these two, the black and the green one, not so much. And we actually have a little bit of an outlier, if you remember, with this observation number 58, that kind of starts to overlap with this other set of observations. So this is exactly the same data set we used before for the EM algorithm. Now, our initialization is going to be very similar again to what we did both with the EM algorithm for the bivariate mixtures and for the univariate EM algorithm, the univariate MCMC algorithm. So the components are initialized so that each one receives the same weight, 1/3, 1/3, 1/3. The means are randomly sampled from multivariate normal distribution in this case. And finally, the value of the sigma associated with each component is going to be the variance in the sample, in this case divided by the number of components. And this aims at, in some sense, avoiding the problem that we saw before with components that are too dispersed, and that slows the convergence of the algorithm. So our initial guess in this case, which, again, you have already seen in previous iterations of this example, looks like this. So we have two components that initially are actually very close to each other, and no component that really captures the points up here in green. So our priors are going to be very similar to the ones we use for the univariate case. Again, we're setting the prior on the weights to be a uniform distribution. We have, this is in this case the mean of the mu's, and because it's a bivariate normal, we need a bivariate normal as our prior for the mu's. So we're doing something a little bit different from what we did before. Before we set it up to 0. Now we're going to kind of do something similar to empirical Bayes or an empirical Bayes light, in which we just use the mean of all the observations as the mean of the means, in some sense. So this is kind of a rough guess. And similarly, we're going to assign as a variance for the means something that is roughly scaled by the variance of the data. And in this case, I have used 10 times that variance. Something around that tends to be a reasonable number. In general, you don't want to use non-informative priors, so you don't want to try to use a flat prior here for the variance of or for the mean of means. That will typically lead to poor results in the posterior. So you want to use something that is roughly scaled to the data, and something like this tends to do a good job in practice. Finally, for the variance-covariance matrices, in this case, we're talking about matrices, not just about a scalar. So we need to use an inverse Wishart distribution rather than an inverse gamma distribution. That inverse Wishart prior is going to have a shape parameter, just like the gamma that we're setting to 2. And then it's going to have a scale matrix, which in this case we're setting to be, again, in a kind of empirical Bayes style, to be the variance of the data divided by 3. Remember, these are your prior guesses, and this will be updated using the data. So even if you were to replace this 3 by a 6 or by an 8, that is unlikely to change your results very much. This is just done so that you can have a rough scale that is matches the scale of the data. Now, in this case, again, just to illustrate how the algorithm works, I will run only 40 iterations, and I will not do any burn in. And what I want to do in this case is to illustrate how the algorithm converges in a similar way to how we illustrated the convergence of the EM algorithm. We can store the values of the samples. This is something standard. If we were going to try to do posterior inferences, we would need those values. And the structure of the sampler is pretty much identical to the univariate one. So the way in which we update the component indicators is precisely the same. In this case, the components indicators are being called XI rather than CC, but it's exactly the same parameter as before. It just tells me which component each observation comes from. The way in which the weights are updated is, again, exactly the same, and this is going to be true. This particular instruction is pretty much going to be the same for any mixture model that we will be using in this course. Then we have a mechanism for sampling the means that, again, resembles a lot what we had done in the past, with a slight variant that now we're working with multivariate normals. So we need to be working with matrix products, inverses, and sampling from a multivariate normal distribution for the full conditional posterior. And similarly, now we have variances that are different for each component, so we need to sample multiple sigma k's, and each one of those sigma k's is going to be sampled from an inverse Wishart distribution. So the structure of the sampler is the same, even if the details for a couple of the full conditionals are slightly different because the kernels are different. The last few steps are, again, the same. So we have, we're storing the posterior samples that we're generating. We're computing the log posterior distribution so that we can track convergence. And unlike in the previous examples, we're going to plot our estimate of the posterior distribution at each iteration of the MCMC. And we're going to try to look at it as a movie like we did with the EM algorithm, again, to see, to illustrate the behavior of the algorithm. Okay, so if I go back and run my algorithm from scratch, it does take a couple of seconds. So we have our 40 iterations. We can see a behavior that is very similar to the one we saw in the univariate case. So our guess is not all that good. So we start with a very low log posterior. But as the algorithm starts to converge, we can see that the log posterior tends to increase until it kind of hits a point where it appears to have converged. And in this case, actually, convergence happens relatively quickly. For our algorithm, that's because the initial point was actually not all that bad. Now, this is the picture after 40 iterations of the Gibbs sampler. In this particular step, you can see that the guess for the components really reflects what we would expect to see and what the EM algorithm was showing us. But we can play this as a movie, and in this case, I'm playing it backwards. But let me go back all the way to the beginning. So as you can remember, this was our initial step, our initial guess. So after one step, the algorithm has decided that it needs to have some components with a bigger variance because it needs to kind of capture these observations that were not being captured by the previous estimate. But this is still a very bad estimate of the distribution. So, but as we take a few more steps, the algorithm starts to differentiate between the two components, and correspondingly, the log posterior starts to increase. Now, unlike the EM, where the algorithm always improves, in the Gibbs sampler, you will see a trend towards improvement, but at some iterations you may actually come down slightly. That is normal. You take a few more steps, and the algorithm starts to identify the locations. And by this point, it has identified the presence of the 3 components. And a couple more steps, it has kind of refined the shape of those components. And from this point on, you can see that the exact shape changes a little bit. That's part of what the algorithm does. It's sampling, so there is going to be some randomness at each iteration. But you can see that the overall shape tends to stay more or less the same. You can see that once in a while, some of the observations get misclassified. So for some iterations, this point seems to belong to this component rather than to this. But in the next iteration, that goes away. And we repeat this. And again, you can see the algorithm fluctuates up and down around a point that is around minus 460 in the log posterior. Until, and what we would do in practice is to drop the first few iterations of the sampler and use the final ones to perform inference in our posterior. And we could have obtained, for example, an estimate of the posterior distribution of, in this case, a bivariate posterior distribution in a way that is very similar to how we did it for the univariate one if we were to run this algorithm for longer.